We can't hear you, Professor.
You're still muted on our end. Try clicking the microphone to select your source. It's probably trying to connect to your headset.
Okay, is that any better?
Yes, we can hear you now.
That's
I
weird.
can hear you.
I don't know why my headphones, the microphone kicked out, but we'll have to figure that out later. So we've got 103 of the 120 or so that are registered. So we're doing pretty good today. So anyway, so this is the first meeting of MSE 3141, which is, of course, required for all the MSE and welding students. It's my first time teaching this class. I've lobbied to teach it for quite some time, and I'm very excited about it. As we'll go through, I think you'll see this class is what I consider the absolute heart of material science, and is really central to what's required for welding as well. So I'm really excited to be able to offer this to you guys. A lot of the material here is something that I revisited in the advanced physical metallurgy course, would revisit in the graduate mechanical behavior course, so it's topics that coming up over and over again. Before we get going with material and syllabus stuff, I would like to introduce the TAs for this course. Alexander, I see, is on. You want to give a quick hello and...
Hello, everyone. My name is Alexander Reichsnyder. I am in my second year, just entering my second year as a PhD student in material science. I work at CMAS, which is the Center for Electron Microscopy and Analysis, and my work has to do with metal organic frameworks and using the advanced microanalysis tools that we have available at CMAS to try to characterize those a little bit more thoroughly. So I'm excited to be helping you with this course. My undergraduate degree is in metallurgical engineering, rather than material science. So even though I have not taken this exact course before, I should be able to help you with anything that you might need. For those of you who knew me last semester, I do apologize for the current state of my hair. It's about 8 months overdue for a haircut, and about 2 months ago, I lost the battle with trying to comb it into submission, and so it's just going to be like this until I feel safe getting a haircut.
I gave myself a home COVID haircut last night, so
Probably should look into that.
Okay, so Kelsey is also on. Hopefully.
Yes. Hi, everybody. I'm Kelsey Spicer, and I'm in my second year of my master's degree. I work over at the Fontana Corrosion Center with trying to develop a coating system for aluminum alloys so they can withstand an ammonium hydroxide environment for ammonia water heat pumps. I did my undergrad at Ohio State, so I did take this course a couple years ago. So I look forward to helping everybody along in their journey through welding and MSE.
Cool. So we will get going. Let me just so I can share this properly. Where did it disappear to? Okay. Okay, so it looks like we're good here. I'm going to try and keep myself up. I know there's a lot of people, myself included, that sort of have difficulty with just the slide. So I'm going to try and keep my face up as well, which Zoom doesn't make very easy. I find I need a lot of cues from sort of the speaker themselves to be able to get stuff. But anyway, so let me reintroduce myself. I'm Steve Nesgoda. I'm a faculty member in material science and engineering, mechanical engineering. My research is very much on a couple different areas. Primarily, I'm interested in microstructure evolution during mechanical processing. So I do a lot of work in recrystallization and recovery, and understanding how do we optimize microstructure by forming and forging processes. I also do a lot of work with steel and understanding martensitic transformations. So this material is really near and dear to my heart. So let's just run through the course outline of what we want to do today. Unfortunately, it's the first lecture, so we have to go through a bunch of administration stuff. So just Kelsey and Alexander, if you guys can keep an eye on the chat with 100 and some odd people on the meeting, it'll be hard for me, especially if I'm trying to lecture, to see if someone has questions or anything. So if you guys can keep an eye on the chat, and one of you sort of break in and interrupt me if there's questions that pop up there. Anyone who has a question they need to ask sort of in real time, just throw a message in the chat so that one of the TAs can see it and let me know. We'll try and keep the cacophony of people down, and then once I sort of know that someone has something, you can unmute and throw it out. So don't be shy about asking questions. Okay, so a couple course administration things. We got to quick look at the syllabus. And then I want to have really a discussion, and we'll see how on earth this is going to work with this many people. But we'll try and have an actual discussion about what this class is about. And then I want to end with some discussion on the concept of microstructure a little bit more deeply. Okay, so course administration stuff. So what do I think that you guys, or what am I assuming that you already have some knowledge on, right? And don't worry if some of these concepts are hazy or you hear them and you're like, because we're going to recover all of these again. But these are things I think are the most important bits from 2010 and 2251 that as MSE folks, you really should have sort of at your fingertips, right? And that basically starts with the basic structure of metals, crystalline ceramics, glasses, and polymers, right? I don't mean that you need to know all of the weird ceramic unit cells. I don't expect you to be able to draw out a anti-fluoride or perovskite unit cell, but you should know the basics of FCC, BCC, HCP, perhaps some of the more simple ionic crystal structures such as rock salt, and a diamond structure for covalent. The basic idea of glasses as amorphous solids and perhaps what some of the packing is, and polymers, right? That polymers, you know, what do we get for structure with these long chains? We should be familiar at least with the language of defects in crystals. We're not going to be talking too much about the structure of them in this class, but we should know what vacancies are, interstitial atoms, dislocations, grain boundaries, and other interfaces. If we talk about things in ceramics, I might talk about other types of charge defects in ceramics as they come up. But we should have at least the idea of defects in crystals. And these are things that you've definitely seen before. Fundamentals of diffusion, right? Fick's first and second law. Parallel with this, the mathematical framework is the same for the basics of heat transfer, right? So diffusion, the previous work on diffusion basically stands as a proxy for all kinds of transport phenomena. Basic phase diagram calculations, what are the equilibrium phases going to be, and how to use the lever rule. The first law of thermodynamics and its applications, entropy in the second law, and the basics of thermodynamic and mixing. And in particular, these last three things will be the subject of a review starting on Friday when we look at some of the key ideas in ceramics. I want to throw out an idea that perhaps this class is a little bit misnamed, maybe. Processing sounds like the emphasis is misplaced, right? The focus of this class isn't on manufacturing processes per se, right? This isn't a class about casting or extruding in polymers. It's not welding. We're not talking about epitaxy. I mean, these are all things that we will talk about, but the focus of them isn't on how to apply processing or the specific details of all of these. What really is this class about? It's kinetics and phase transformations. Maybe that might be a better name. We can discuss it. But really the focus is on our fundamental materials physics, right? And what is the physics underlying changes in our material, right? We're not going to be so much focused on the method of applying the driving force, right? If I were to say develop a course that I would call materials processing, I would have things like focusing on calculating friction factors and mixing coefficients for extrusion processes, for polymer extrusions, or things like die casting or injection molding or hot rolling of steel, or vapor deposition for semiconductor, right? Those are all processes, and getting into the details of those would be sort of what I would consider a processing course. Here, we're really sort of focused on the material itself, right? Understanding the evolution of microstructure that occurs during the processing of materials. And this might sound like a sort of a distinction without a difference to you right now, but hopefully as we go through the course, that the reason why I threw this out front will be a little clearer. Okay, so what do I hope that you get out of this? All right, so after completing this course, I'm hoping you guys have a good basic working knowledge of the application of using phase diagrams to predict microstructure, and what are the limitations of microstructure prediction from phase diagrams. And those limitations are a big reason for the need for this class, and that'll be part of our discussion today. Understanding the mechanisms that underlie solid state diffusion. A lot of our phase transformations that we're going to talk about are diffusional phase transformation. They depend on the relatively long range transport of chemical species from one part of the material to another, and the rate of that transformation is often directly limited by the rate of diffusion in the material. So having a good working understanding of the mechanisms plus the mathematical analysis, the quantitative equations that come from first and second law, and these are will take the form of solutions to partial differential equations under specific sets of boundary conditions. So then we'll move on to the mechanisms of phase transformations in material: solidification, vapor deposition, diffusional and non-diffusional transformations. So diffusional meaning things like nucleation and growth of second phases, and of course non-diffusional, the most prominent one being martensitic transformations, right, where we have a shear transformation from one state to another. What are the kinetics of these various phase transformations? And this kinetics is the really the key concept and the focus of our discussion later on. And of course, the microstructure evolution during processing and the relationship to material properties, right? So this is really what the course is about, what I hope that you guys are going to be able to get out of it. So there's a couple things you should know by heart by the end of this class, okay? No matter what you're studying, whether you're going to metallurgy or functional materials or welding or polymers, I think everyone expects every material scientist to know the iron-carbon phase diagram, right? Steel is just way too important in our universe to not know this. If you don't know it now, you will know the lever rule, the Scheil equation for solidification, the enthalpy balance for cooling curves, of course, Gibbs phase rule. I'm sure that Professor Akbar hammered you pretty hard with this in thermo. Fick's first and second laws, the Arrhenius equation, to understand the temperature dependence of diffusional coefficients, and why on earth something that's related to mobility takes the exponential form of the Arrhenius equation. The common tangent construction that allows us to take the Gibbs free energy curves and construct phase diagrams out of them, and JMAC, basic JMAC kinetics for nucleation and growth, right? So maybe just a poll by hands, or I guess there's too many people, I can't actually see it. So maybe throw this, if this list looks really surprising to you, or there's a lot of things that you haven't heard of, maybe throw a message or so up on the chat, just so I can have a sense of what whether or not, or I guess how familiar you guys are with this list coming in. Okay. We're going to go through the syllabus, but what's critical for this class, right? the biggest thing I want to say is the reading, right? It's okay if you don't understand it 100%. That's perfectly fine. But doing the reading before lecture is really critical. The first reading quiz will be on Monday. We'll talk about that in the syllabus. Basic attendance, asking questions. Really, the biggest thing that's going to affect your grade is deadlines on quizzes and the homework are going to be strictly enforced, because with a class of this size, I can't really keep track of a lot of exceptions. So don't miss quizzes and homework, right? And all the lectures are recorded, so you can easily revisit topics that you have have difficulty with, right? So I do see Scheil equation or JMAC, that's fine, and the common tangent construction. So the common tangent construction is really interesting. It's a couple people put in chat. This is something that a lot of people in ModSim, the junior level modeling and simulation class that you guys will be taking in spring, last year said that they've never seen before either. About 80% of the class stated they weren't familiar with it, so I asked Professor Akbar, and of course he immediately gave me the notes of where it was taught in 2251, and I reposted that, and then everyone was like, oh yeah, I've seen that, and completely forgot about it. So this common tangent idea is something that I taught from scratch in the graduate level metallurgy class, simply because most people just forget it. It's like something in their brain that says this is something that can go. So it doesn't stick. We'll cover it again from scratch here. Okay, so let me switch over to the syllabus. I'm sure every one of you has read it deeply and knows all the details, but just for the sake of having it on record that we talked about it, we'll scroll through some of it. Okay. We know what class this is. Of course, it's going to be primarily synchronous online. You know who I am. The TAs have introduced themselves. We have, of course, the Zoom links. So my office hours are going to be starting next Wednesday from 12 to 1. The link to get to the Gather site that we're going to be using is here. If you haven't played around with Gather, give it a little shot. The idea behind using Gather rather than Zoom is that it's more social, in the sense that then we can have small groups together, and me and the TAs can, for their office hours, can move easily between the groups, and people can still continue to work together. Alexander and Kelsey will be hosting another set of office hours at a time to be determined. That's based around their class schedule and yours. So before this 12 to 1 is flexible. If anyone has a major, if a large chunk of people have a major course conflict, just throw it in the chat, and we can find another time for this. Okay. So the mode of delivery, all right, of course, it's this online synchronous manner. There will be a reading quiz most Mondays. I'm going to be taking attendance at the beginning or sometime during each lecture via Top Hat. So the Top Hat join code and everything are on Carmen. And it should be, oh shoot, I didn't put it here. Anyway, the Top Hat code is on Carmen. All right. And then we have online homeworks. And we're also going to have these idea of mastery-based assessments via Carmen. And I'll talk about what that means in a little bit. Exams will all be take home, open book, open notes, essentially open Google. I don't care. And my phone just yelled at me when I said Google. Okay, so reading. Oh, the other thing as part of the reading is I'm asking everyone to post on Carmen as an assignment, actually, a question or critical comment on the reading, right? So I want to know, what is your muddiest point in the reading that I assigned, right? Or if it was really easy and everything was clear, you can post, this was really easy, it should have gone more in depth here, right? But these are graded based on just doing it. I'm not going to attempt to grade the content of these, but these are really for me to help guide the discussion during the lectures coming up, and as just sort of another check on that, one, everyone's doing the reading, and two, that to get a sense of what's going on. Homework is traditional written problems, submit via PDF or other digitized copy of your work. Cell phone pictures are just fine if you don't have access to a high, a flatbed scanner. Right. There's going to be lots of math, so you do not need to typeset your work per se. You don't need to put it in Word. If you're savvy and fast, you can do LaTeX, but you absolutely don't need to. Handwritten with clear cell phone images is sufficient for turning things in. These mastery-based quiz are for each topic, each module, we're going to have a small number of questions that are going to essentially help you assess your understanding of key concepts, right? So if you are getting these questions correct and progressing through them, it means you can be confident that you have a pretty good understanding of what was taught. If you have a hard time completing these, then it means maybe you should go back and look at some of the lecture or focus on the homework a little bit more. But anyway, these have sort of a long open period. You have about 2 weeks following the end of the module to complete these questions. And it's graded just on your completion of them, right? And they'll be like homework questions, but not as difficult. Okay, so we'll have 2 take-home exams, right? You've got 24 hours to complete the exam, perhaps longer. And they're going to be fairly similar to homework questions, but probably a little bit more difficult, right? So expectations. This is a 3-credit hour course. You guys sort of by now have a sense of what the expected workload is. Okay, so the book assigned for the class, this is an older edition. You probably have the blue one if you bought the most recent one. Any version is suitable. Buy, borrow, steal. A copy, you do not have to have any particular version. There is no digital code. You don't need it for online homework or anything like this. I want to say that this book is not perfect. It's limited in scope to metals, right? So the fundamental theory is universal across all materials, but the examples and homework in this book are all focused on metals. The level of writing, I think, is pretty appropriate for junior level MSE students. However, it is a perpetual criticism that the book is hard to read and hard to follow. It also has a lot of typos and errors that have not been fixed in the newest edition. They just added new errors. But that being said, it is the best book at the undergraduate level that is currently available. I'm going to be posting a bunch of extra reading materials from additional sources to supplement that. Some of those readings will come from Fundamentals of Ceramics from Michel Barsoum, Kinetics of Materials. This is a PhD level book, but there are sections of it that I will be taking things out of, and I'll be taking examples out of here as well. Some others, I'm sure everyone has a copy of Gaskell from Professor Akbar's class. This is an older edition, but Swalene, Thermodynamics of Solids. This is an out-of-print book. It's also really good, and it also is chock full of errors and typos. I don't know what it is with these books, but I'll be taking some reading out of here and noting when the text is incorrect. Polymer stuff will be coming from this book, Fundamentals of Polymer Science, Painter and Coleman, right? So and then a whole bunch of other external articles. So there'll be a lot of stuff that we'll be adding. Top Hat will be used for attendance. I forgot to add the join code there. And then the rest of this stuff is, all right, grading. Okay, so Top Hat attendance in this reading question submission is 5%. 15% for reading quizzes, I'll be dropping one of them. Homework's 20%, we'll be dropping one of them. Each of the 2 exams is also worth 20%, and then 20% for the completion of these mastery-based understanding questions. So essentially, the way I look at it is if you do the bare minimum, right, and just show up and do the reading, you've got this 25% is a complete gimme. Right, so, but it's a big enough portion that if you don't do it, it can totally. Oh, okay. So Professor Akbar you didn't have to buy Gaskell, but anyway, I'll be extracting some additional reading from there as well. What book did you guys use for Thermo then? I'm sure, or did you not have a textbook that you had to purchase?
We didn't really have a textbook. He just posted like a bunch of PowerPoints chapters online.
Okay. That's good. The book's expensive, and you only use about 1/4 of it in sort of a freshman or in sort of a sophomore level thermo. Okay. The rest of this is essentially boilerplate that you know of: Title IX, bias, mental health. Right. There's a lot going on, guys. Right. If you need anything, there's resources available. If I've received a couple SLDS accommodation requests. If you have any other additional accommodations, please talk to me. Okay, so that's basically that stuff, the key points there. We have a couple minutes, and so I'm going to actually try something, and we'll see. This might be a complete and total disaster. But I'm going to stop sharing on this computer, start sharing on this one so I can. Okay. Hey, this actually appears to be working. Now, where did my Apple Pencil go? There it is. Okay. So this might sound like a really goofy question, but what the heck is material science? What defines material science as a discipline, and what makes us different than solid state physicists? All right. So everyone is in this class is ostensibly in the material science department. So what do you tell your grandparents when they ask you what you're studying? So someone brave chime in.
I tell my parents usually that it's the physical composition of, well, anything, materials. And the reason I think it could be different than physics is that it's a lot less theoretical at times, a lot more practical.
Okay, so physical composition. Okay. So can you explain what you mean by physical composition?
What I mean by physical composition is whatever something's made of, it has certain properties. Like, say, if it's aluminum, it will be stiff, it will be light, it will have a metal structure, it will.
Okay. Okay. So I'm going to make an argument, right?
Mm-hmm.
You said
Okay.
the word, you said, I think, a key word here. Structure.
Mm-hmm.
Right?
Yes.
So I'm going to make an argument and say that, or ask, I guess maybe ask a question, right? So is composition, do we know everything we need to know about a material just based on its composition and
No.
current conditions?
No, because let's say you needed to build a structural beam for a building. You could have like a pile of iron scraps and get composition and conditions from that, but without knowing like the structure of the actual beam you need, it would be useless.
Okay, so by structure, we can define that further and say microstructure.
Yes.
Right? So if we have a chemical composition, let's call that the genetics, right?
Okay.
Right. But we do know that it's not, in people, there's this debate of nature versus nurture, right? How much of a person's aspect comes from their genetics and how much of their personality comes from how they were raised, right? And the environment that they grew up in, right? And their personal history, right? And so, and for a material, we also have this notion of processing, right? And so that we'll call the epigenetics, right? Or the nature versus nurture, right? So the material science is dealing with not only what the material is, but how it was processed. What might be another way of expressing that? So, okay, so apply our knowledge to not only design, but also to make. Other domains of engineering, properties of material science. Ooh, that's interesting. Right? So there's a old joke of the material scientist doing all these tests and writing on a piece of on a hunk of metal, doing all these tests and all these measurements, and then writing 5 numbers into a mechanical engineering design handbook and passing it off, right? So that's an interesting observation from Anthony there. What I would also like to think about is how does this processing affect the material, right? Why does this epigenetics or nurture matter? Why is microstructure important?
Because like the material with identical composition, but different microstructure will have vastly different properties. So an austenite microstructure will have a lot of different properties, like non-austenite. Like what's the one with M? Yeah, but so like depending on how it gets, depending on how it gets there, it'll have very different properties.
So properties are a mathematical function of the microstructure and the processing.
Yeah.
Is it another way of saying that, right?
Yeah.
Macroscopic properties arise from microstructure. Features. Okay. So, but what is changing in the material as you alter the microstructure that gives you different properties?
It's in stuff like grain size and like stuff like that. I'd say of it, right?
Yeah.
And then I assume I'm sure depending on processing, you can get different amounts of interstitial, just different types of dislocations or not, or I don't know, right? Something like that.
Yeah. Right. You're hitting, I think, now on the primary, what I think the primary difference between material science and solid state physics is, right? Solid state physics, you're most of the time interested in the intrinsic properties of a single of a material, right? What is the conductivity of graphene, say, right? Or a specific semiconductor device, right? Where for the most part, right, folks in material science tend to be interested in optimizing a defective structure, right? And what do I mean by defective? I mean, you hit on dislocations, you talked grain size, right? Interfaces and phase compositions, right? Having a composite material where I have multiple thermodynamic phases is really dealing with a defective material. And how do we harness and optimize this defective structure is really what makes material science, right? So the next sort of, in the last 5 minutes, I want to talk about thermo versus kinetics, right? And I want to ask the big question is, oops, what is missing from thermo, right? Why do you even need this class when you've had thermodynamics? So there's a question that just popped up that says, do you have a full 24 hours to complete the exam? Yes, it is a take-home exam, right? Right, I give it to you, a day later you turn it back in. So, okay. So this course, yeah, you get 3 credits towards the major. But I said before, oh, I think Nathan just hit on it, right? So do you go by Nate or Nathan? You can either throw it in chat or
I usually go by Nate.
Nate, okay. So it's time, right? An equilibrium phase diagram doesn't tell you anything about how long it takes to get to equilibrium, right? If you look at a phase diagram, diamond wants to be coal at room temperature and pressure, right? It's deeply metastable. The kinetics of it are such that it's not going to, a diamond ring is not going to change back, right? Table sugar is not thermodynamically stable at room temperature, right? But no one worries about their sugar bowl exploding, right? Unless you put an oxidizer like potassium permanganate in it or something. But, right? So time is the first thing. Also, all of last semester when you took thermo, what was the assumed state? Right? I guess you can divide thermodynamics into 2 big categories: equilibrium thermodynamics and non-equilibrium thermodynamics. What was everything that you guys talked about last semester? Right. So Jason, yeah, everything was, you guys talked about equilibrium, right? Non-equilibrium thermodynamics is exceptionally complicated. But let me ask you, the question is, when you're at equilibrium, is there actually any driving force for a change? Right? If I take water, pure water, and I take it down to exactly 0°C, and I put some ice cubes in it that are also, right, the ice will warm up to 0°C. Will it melt or will it just sort of hang out? Right? It's not gonna do anything, right? I have a perfect equilibrium between water and ice, right? It's not gonna go anywhere. If I now throw ice cubes in warm water, right, we all know they're gonna melt, right? But is that change reversible anymore? Right? It's not. I now have a non-equilibrium situation, right? Cooling, solidification of metal, vapor deposition for PVD processing, any type of material processing happens under non-equilibrium conditions, right? And in fact, you need, we'll talk about this in detail, if you want a phase transformation to occur, you need to move it away from thermodynamic equilibrium, and the farther from equilibrium you are, the greater the driving force, right? That's the magic behind supercooling of water, right? You freeze liquid water down, you cool liquid water down enough, and if it's in a clean container, the requirements to form a nuclei are such that it prevents the water from freezing, right? But if you get it down low enough, cold enough, you overcome that barrier, right? You have enough driving force to freeze that you can overcome the nucleation penalty and freeze out your water, right? So really here, everything that we're going to be talking about is largely under non-equilibrium conditions, right? That doesn't mean thermodynamics isn't going to be useful, but it's only one part of the whole story. Okay, so I'm out of time for today. I'm going to stop there. We'll talk about microstructure a little bit next week, or on Friday, sorry, and we'll also go into a bit of a thermo review, right? So have a good one, and we will talk to everyone then. Okay. How do I stop sharing?